Hello, everyone. I am Dr. Jet Aguilar from the Astronomical League of the Philippines, and I will be hosting this webinar. Thank you so much for joining us for our 2024 Astronomy Expert Speaker Series. I am very happy to welcome all our attendees, not only from the Philippines and Southeast Asia, but also from all other parts of the world. For our 139 plus registrants, I see names coming not only from the United States, also from Canada, United Kingdom, France, Czech Republic, and even Montenegro. Thank you so much for attending, and I hope you will enjoy today's webinar. We have quite a sizable number of registrants today because we do have a very exciting and interesting topic to be discussed by none other than Dr. Brad Schaefer, a Professor Emeritus of Astronomy and Astrophysics at the Louisiana State University. Brad will talk on the recurrent nova T Coronae Borealis, which is expected to explode at any time now. My fellow ALP member, Mr. Edwin Aguirre, will be doing the introduction for our esteemed speaker. For those who were not able to register, but will still want to watch, we would try to do live streaming on Facebook at the Facebook page of the Philippine Astronomy Forum, where you can also view this webinar live. Before we start, kindly allow me to explain some rules for this webinar to help us make this an enjoyable learning experience for everyone. Please listen and do your best to give your undivided attention to our speaker. There will be a short question and answer session at the end of the presentation. You may type in your questions under the Q&A tab found in your Zoom interface at any point during the presentation. We will do our best to read and answer questions live after the lecture or via the Q&A tab. We would like to remind everyone that the contents presented in this webinar will remain as the individual property of the lecturer and the photographers in the presentation. We will also be distributing certificates of attendance via email to all registered attendees who will be present throughout the webinar. So please use the name you have written in your registration forms to help us facilitate this process. Enjoy the webinar and let us all have fun learning. Here's the program flow for today's lecture presentation. May I now turn you over to Mr. Edwin Aguirre for the introduction of our speaker.
Good morning and good evening to everyone. We would like to welcome you to our Astronomy Experts Speaker Series. It is my great honor to introduce to you our distinguished speaker for today, Dr. Bradley E. Schaefer. He is a Professor Emeritus of Astronomy and Astrophysics at Louisiana State University in Baton Rouge, and he received his Ph.D. from the Massachusetts Institute of Technology in 1983. I first became acquainted with Brad 26 years ago in 1998. As an associate editor of Sky and Telescope magazine, I edited Brad's feature story entitled Meteors That Changed the World. It was such a pleasure working with Brad on this article, which was published in S&T's December 1998 issue. Now, Brad has a knack for great storytelling and detective work. And so he authored other wonderful feature stories in S&T with titles such as Lunar Eclipses That Changed the World, Solar Eclipses That Changed the World, Sunspots That Changed the World, Comets That Changed the World, and Conjunctions That Changed the World. So if you can go to the back issues of S&T, please try to read them. It's very informative. Now, you see, Brad has a wide range of interests throughout astrophysics, including gamma ray bursts, supernovae, supernova remnants, supernova progenitors, historical records of supernovae, novae, recurrent novae, superflare stars, low mass X-ray binaries, eclipsing binaries, Nereid, Pluto, Kuiper Belt Objects, sunspot counts, and archaeoastronomy, to name a few. Now, Brad is a member of the Supernova Cosmology Project that co-discovered the acceleration of the expansion of the universe and dark energy. Now, their work was recognized with the $3 million Breakthrough Prize in Fundamental Physics in 2015 and the $500,000 Gruber Prize for Cosmology in 2007. The project's team leader, Saul Perlmutter, shared the Nobel Prize in Physics in 2011. Brad attended the Nobel Prize award ceremony that year in Stockholm, Sweden. Ladies and gentlemen, please welcome Dr. Brad Schaefer.
Well, howdy. Can you hear me? Should I start screen share?
Yes, thank you.
There we go. Is that all on my first screen visible and audible?
Yes, it is.
Okay, there we go. Hey, so today I'm going to be telling you the story of T Coronae Borealis. Well, I'm going to keep calling it T CrB, but well, there you go. Coronae Borealis is the constellation that's between Boötes and Hercules. It's a nice little circlet in there, well, much like you can see here. And T CrB appears, it'll appear as a nova just a little bit off to one side. And when it comes, it's going to be brighter than the alpha star there, Alphecca, and it's going to be one of the brightest stars in the sky. It probably is going to be just barely first magnitude. Okay, so let me tell you the story of T CrB. Well, the story actually does not start in the year 1842, when the great John Herschel claimed that he might have seen an early eruption of T CrB in the year 1842. But I was able to go back and prove that John Herschel's star was not T CrB. Herschel was one of the all-time greatest visual observers, but he did not catch a T CrB eruption. So our knowledge of T CrB starts in the year 1855, when the great Argelander was preparing the Bonner-Durchmusterungen catalog. This was getting brightnesses and positions for all stars down to 10th or 11th magnitude. Argelander is another interesting person, and he also, with his Bonner-Durchmusterungen work, is one of the all-time greatest visual observers also. He's up there with John Herschel, and actually also with William Herschel is another greatest of all time, or one of the greatest of all time. So Argelander recorded the star we now call T CrB as a faint star around 10.4 magnitude. Okay, nothing much was done with it until 1866, when the Blaze star blew up again. And the story starts with another non-detection, and that's by Julius Schmidt. He's the guy pictured there. And Julius Schmidt is yet another one of the greatest all-time visual observers in astronomy. And he worked out of Athens, Greece, and that particular night, he was intentionally scanning the skies, and he checked out Coronae Borealis, and he determined at the time that there was no extra star brighter than 5th magnitude. But a couple hours later, a variable star observer named Birmingham actually it was in Ireland, excuse me. In Ireland, a couple hours later, Birmingham found this star, that there was a new star in Coronae Borealis at the brightness of, well, it peaked at 2.0 magnitude. So there's a couple hours in there. And so this new star, this nova, now called T Coronae, had to have brightened by huge amounts, at least 3 magnitudes in a couple of hours. So it was very fast brightening. And here's the light curve of it. And it not only had a very fast rise from Schmidt's limit up to Birmingham's point, but it also faded away very fast. It was at peak magnitude, say within a magnitude of peak, only for half a day, 1 day, something like that. It's fading really, really fast. And in fact, by the time it fades below 6th magnitude, which is naked eye, the traditional naked eye limit, it faded that fast in only 7 days. So the T Coronae eruptions are really fast. They're short in duration, and for the upcoming eruption, you're going to have a relatively small duration, only a few nights at which you'll be able to see it with the unaided eye, and only 1 night or so when you'll be able to see it at peak. Now, when Birmingham made the discovery, other people made the discovery too, and the news of this discovery got passed around very widely. And so astronomers started observing it. Well, here's a light curve. This is representing all of the observations of people, and it was very well observed. The total duration was like 30 days, 40 days, depending on where you call the limit. And it was all over with and done with fast. Now, T Coronae is the first classical nova ever seen, much less one that is measured and observed and recorded this well. Well, in fact, T Coronae is the first nova, among the first of anything, that where people actually got a spectrum of it. And this was by Huggins in England, and he effectively just put a prism up to the eyepiece, and he could see the light spread out into the colors. And he noted a variety of emission lines and so on. He didn't know what to make of it at the time. Now, the eruption of T Coronae, it's the first, well, people back for millennia had observed transient stars, new stars up in the sky, but we now know that they are all supernova or other things. And so T Coronae is the first nova that was actually seen, and it was very well observed. This made a big deal in the press and the populace at the time. This was mostly before names for variable stars had been canonized. And so T Coronae got called the blaze star. You have a star blazing up in the sky. Well, the T Coronae is the blaze star. Well, after the 1866 eruption, it did something weird. It had a secondary eruption. Okay, so here's a light curve. This is a little bit extended. This light curve right in here is the primary, it says secondary eruption. This is the primary eruption. That's a typo, effectively. This is the primary eruption up in here. And this is what I'd showed before. And the eruption went back to background after about 30 days or something like that. And it stayed at its normal quiescent brightness for, near up to 100 days. And then it did something that has never been seen, well, before or since. And that is it re-brightened again. It brightened from about 10th magnitude. It brightened up into the 7th magnitude range. And it stayed bright for about 100 days or something like that. And if we didn't have the primary eruption, you would call this as being, well, another nova eruption. So this is a secondary eruption, and it is completely unique. Nothing has ever been seen, anything even vaguely like this. And it's still a mystery. What on earth is going on with this? We don't know. And that's one of the things we'll hope to learn coming from the new eruption. Maybe we'll be able to get enough observations to work out what this secondary eruption is actually, what it actually is. Now, you can see that people, the observations, the brightness of this, people kept following T Coronae, well, for years to come. Okay. And it turns out people followed this for, well, decades to come. One of the longest and best records is that by Julius Schmidt. You might recall he's one of the greatest of all time visual observers. And he followed it actually up until, I think it was the 1890s, if I remember right. Okay, people kept following it, but people really didn't know what to make of it. Okay, I should back up here and mention that at the time, well, T Coronae was the very first nova ever seen, and people had utterly no idea what a nova was. It was, you can read their speculations, and their speculations like a, well, in modern light, they don't make much sense. But they were struggling at the time. They were struggling to try and figure out what on earth could cause a nova brightening up in the sky. Well, in the continuing observations of T Coronae, they kept on going and going. And T Coronae in quiescence, it trundles around 10th magnitude, something like that. And there's flickering on it. So there's fast and slow variability, but the T Coronae remains basically the same brightness. Now, starting in 1920, Leslie Peltier started observing T Coronae regularly. Here's a picture of Leslie Peltier at one of his telescope. This is the telescope in Delphos, Ohio, a very famous telescope because it was used by Leslie Peltier. Now, Leslie Peltier is one of the, yet another one of the greatest of all time visual observers. Well, Peltier's been dead for a number of decades. And even today, there aren't that many, or even today, there are, I know of only one living person who would qualify for being among the greatest of all time observers. Well, Jones in New Zealand died about 15 years ago. So the only person I know of who would qualify for being among the greatest of all time visual observers would be Steve O'Mara. And Steve O'Mara is an old friend of Imelda and Edwin. He was an editor at Sky and Telescope around about the same time. Anyway, for Leslie Peltier, one of the things he did was come up with he wrote a book which is heavily influential called Starlight Nights. I'm holding up a copy. I think you can see it, or I hope so. But he's best known for making a gazillion, well, comet discoveries and variable star observations. So he's one of these people that back in my youth, he was always held up as the ideal. But for T Coronae, he started observing it in 1920. And he tells us that he had this strong feeling that T Coronae would do something spectacular. And he wanted to be in on it, so he kept observing it nightly and frequently. But for, well, 25 years, T Coronae was just trundling along, varying a little bit up, varying a little bit down. Then, starting in 1945, T Coronae started fading, and fading by a lot. It went from its usual, round about 10th magnitude, it got as faint as 12th magnitude. It faded by 2 magnitudes. That's getting up near a factor of 10 decrease in brightness. And Peltier detected this and recognized this, and he realized that something weird was going to happen. So he wrote an IAU circular notifying the world that something was going on. There was this fading here. Well, actually, at the time, it wasn't an IAU circular. It was called a Harvard announcement card. Okay. Anyway, Peltier knew that something was afoot, something was stirring in T Coronae, and it could do, well, anything. Okay, so he has this alert that in 1945 that T Coronae is doing something special. And then the blaze star blazed away again. This is in 1946. This was on a night, 9th of February of 1946. It was first discovered by a guy named Kamenchuk. He was in Siberia, and he caught T Coronae at a magnitude of 1.7. Okay. Now, we don't know much about this observation. I've shown here from the IAU, the 6 lines we have from the IAU circular, which doesn't give much more than just the bare bones observation. This is at the height of Stalinist Russia, and it's hard to get any information out of there. And I don't think anyone has succeeded in actually discovering, getting more information about this one observation. Anyway, Kamenchuk discovered the blaze star blazing away again at magnitude 1.7. Now, the time it takes for the Earth to rotate from having T Coronae high overhead in Siberia until it's high overhead around about Europe was about 5 hours, something like that. So 5 hours later, a guy named Knight discovered T Coronae in eruption. It was an independent discovery. He's a well-known variable star observer, and he was looking in the Coronae area, and just past midnight on February 9th, he found T Coronae at a magnitude of 3.4 magnitudes. And over here, we have his report to, let's see, this isn't the report to the Astronomer Royal, this is the report to BAA, the Variable Star Section at the British Astronomical Association. Okay, and well, he found it. So you see what we have here is we have showing that T Coronae is fading really very fast in those first few hours, because over 5 hours, it went from a brightness of 1.7 all the way down to a magnitude of 3.4. Wow, that's a factor of, that's 1.7 magnitudes in just a few hours. T Coronae fades really fast. Anyway, the Kamenchuk discovery has been little recognized by most people because there's little information about it, and the discovery is hidden in a late IAU circular. So Knight is often credited with being the discoverer. And at this point, you got to think, well, what happened to Leslie Peltier? Okay, so there's a picture of the front cover of the Starlight Nights, that very influential book of Peltier. I'm holding up my copy right now, and let me give you a reading. It's almost poetry, but a reading from Starlight Nights. This is Peltier writing. My affair with T Coronae was not a happy one. Of all these old nova, T Coronae seemed to me the most likely to quaff the enchanted herbs of renewal. The star was an easy one to observe regularly, as it was located far enough north to be visible at some time nearly every clear night. From 1920 on, wow, I watched it closely at every opportunity. For more than 25 years, I looked in on it from night to night as it tossed and turned in fitful slumber. Then, one night in February 1946, it stirred, slowly opened its eyes, then quickly threw aside the draperies of its couch and rose. And where was I, its self-appointed guardian, on that once-in-a-lifetime night when it awoke? Well, I was asleep. I had set the alarm clock for 2:30 a.m., intending to get up and observe some early morning variables. Self-pity comes easy at 2:30 on a cold February morning. So I went back to my warm bed with the comforting thought that I owed it to my family, at least, to take care of my health. And thus, I missed the night of nights in the life of T Coronae. Nevertheless, I still have a feeling that T could have shown me more consideration. We'd been friends for many years. On thousands of nights, I had watched over it as it slept, and then it arose in my hour of weakness as I nodded at my post. I am still watching it now, but now it is with a wary eye. There is no warmth between us anymore. Oh gosh, this has got to be kind of one of the worst nightmares you can think of here. And well, there you go. That's Peltier. Peltier kept observing it until I think it was 1976 that he had observations up until. So let's see, 1976 minus 1920. So he was monitoring T Coronae for 56 years. Well, after the 1946 eruption, people, of course, very intensively following it. And here's the light curve for it. The blue dots are for the blue light curve for 1946, but the two shades of green dots are for the 1866 eruption light curve and for the 1946 eruption light curve. And you can see that the two shades of green dots lie on top of each other. In other words, the secondary eruption of T Coronae was identical between, well, 1866 and 1946. And this is going to be a little bit of a help to us later, because we're going to be seeing similar weird things in the T Coronae light curve. And we now have from this some expectation that T Coronae is going to be doing the same thing from eruption to eruption to eruption. So people kept following this T Coronae, and the news of the eruption made it very far and deep in the world. After all, this was the brightest nova of its generation, and the news, the fame of it, spread broadly throughout the world. As an illustration of this, let me tell you the story of a farm girl from West Virginia. She was young and was just starting a career as a striptease artist. Well, there's a picture of her. Okay, there we go. And just at the end of this eruption here, she chose the stage name of Blaze Star. Well, it's the same thing as Blaze Star, except she added one extra R to the end. And so this is clearly a reference to the fame of the Blaze Star. And I take this as a demonstration that the knowledge and information about the T Coronae eruption trickled down to in popular culture widely and deeply. Now, Blaze Star went on to become well, one of the most famous world striptease artists in the world, and they even made a movie out of her life. It's called Blaze, and Paul Newman was one of the chief actors in the movie. And so you know you're famous when they make a movie out of your a biopic, a movie, a biography of you, starring Paul Newman. So again, this is just pointing out how the prior eruption of T Coronae was broadly and widely known. It's a little bit of a lesson for us, because the upcoming eruption of T Coronae will probably also receive similar publicity and understanding and knowledge around. So history just keeps repeating itself. We're going to be going through the same sort of things here presumably within a year. We'll get to this. Now, for nova, let's backtrack a little bit, because continuing on historically in order, well, in 1946, people had no idea what T Coronae was doing. It was a nova. You could describe what it looks like, but you had no conception of what it actually was. Round about that time, a little bit earlier, people were speculating that nova might be when you have an ordinary star and you have a couple asteroids hitting onto its surface, causing an explosion. Well, that seems pretty naive with modern lights, but it shows that they had no idea, and they were grasping at straws, trying to find something that could explain a star brightening by so much for a few weeks. This all changed back in the late 1960s. Robert Kraft and colleagues, Mumford and others, discovered that novae were actually close binary stars. They found this because some of the nova were eclipsing, which means it's a binary star. And in other cases, they also found that they could get the radial velocity curve, which shows that the stars were coming and going regularly. They were nova. And so the nova consists of two stars in a binary orbit around each other, where one of the stars, the companion star, is a normal star, and the other star is a white dwarf, which is a very small, a way of looking at it. It's the end product of stellar evolution. Our sun's going to become a white dwarf. And white dwarfs typically have the mass of our sun in a volume the size of our Earth. And that requires it to be incredibly dense, which means the surface gravity is incredibly high. Okay. So that's the basic setup. You have a binary with a normal star going around a white dwarf. And the two stars happen to be sufficiently close in orbit around each other that gas from the normal star can start falling off onto the white dwarf. What's going on, and that's pretty simple, is you have this the gas right at the tip of the point here has an equal gravity from the white dwarf as it does from, well, the rest of the normal star itself. So a gas thing here can fall off and, well, it goes into a circular orbit before it spirals down onto the white dwarf. And this is called an accretion disk. Fair enough. And matter falling off the red giant goes into the accretion disk, spirals in, and lands on the white dwarf. Okay. So what you have is the white dwarf is accumulating matter. You start off with an ordinary white dwarf, and you start piling gas on it that falls off from the skies from its point of view. It falls off and creates a layer of accreted gas on the surface of the white dwarf. Okay. And the gas keeps falling and falling, and you start accumulating a lot of mass on the surface of the white dwarf. Okay, well, when you start piling mass on, the pressure at the bottom of the accreted layer becomes higher and higher, and it becomes hotter and hotter. And as time goes on, you accrete more and more matter. The temperature at the base of this layer of accreted gas becomes hotter and hotter, and pressure becomes higher and higher. And at some point, you reach the kindling temperature of hydrogen. Ha! And once you do that, then hydrogen fusion starts a runaway chain reaction. Once you have a little bit of the hydrogen burning, it then creates a lot of heat, which then allows more hydrogen to burn, and this is a runaway reaction. It starts burning very fast. Now, the physics of this nova eruption is close enough. Schematically, it's identical to the hydrogen bomb. The hydrogen bombs are the supers that you hear about in the movie Oppenheimer, and what you have is the whole layer of accreted gas, of accreted hydrogen, starts burning, and there's incredible energy releases. And a good word for both H bombs and for nova is you can call them hellfire. I wasn't cussing there. Hellfire is a separate word. There we go. So a nova is just a hydrogen bomb spread around the surface of the white dwarf. It releases huge amounts of energy, and that's very hot, and that it's an explosion. And the explosion blows away the outer surface of the white dwarf, which expands a large amount of shell. You can see people watch the shells expanding, and it's the expanding shell which creates the bright light, which we see as a nova. Well, after a while, the expanding shell keeps expanding and it dissipates, it gets far away and it fades, it cools, and the nova light turns off. Okay, the nova is over. Well, but you're still left with a situation where you have a white dwarf just sitting there. It has all the accreted gas blown off, but it's still sitting there, and there's still matter falling onto it. So you have matter accumulating yet again on the surface of the white dwarf, which again gets piled higher and higher until it reaches the kindling point of hydrogen again, and you have hydrogen fusion or runaway effect, and you have another nova eruption. And then you start the whole cycle all over again. So novae are all recurrent. Well, let's take a picture of T Coronae itself as a binary star. Let me tell you the things that can, you should be closing your eyes now and thinking what it looks like. Well, if we were in a spaceship traveling close to the T Coronae system, what you'd see is a big mother red giant star, and it's in orbit around a white dwarf, and it goes around in, well, 227 days. We know that period from the ellipsoidal modulation and from the radial velocity curve. So in a little under a year, the two stars go around each other. The red giant itself is about 1,000 times the luminosity of our own sun. It's a big mother, okay? Now, the red giant has on its near edge, on the inner part of it, it's spilling mass over onto the white dwarf, which goes around in an accretion disk. And the accretion disk itself is big and hot and bright. The accretion disk itself is about 1,000 times the luminosity of our own sun. Okay, so this is a very bright system in here. Now, the total mass that falls over onto the white dwarf is about, well, 1 Earth mass in about 50 years. Well, that sounds like an awful lot, a whole Earth mass of gas falling off in 50 years. And it is actually quite a lot. T Coronae has one of the highest accretion rates of all such stars. That's why it recurs. We'll get to that later. But on the scale of stars, an Earth mass, it's a millionth of a star mass. So the total amount of gas which is falling onto the white dwarf is very small on the scale of stars. Well, but 1 Earth mass of matter in 50 years, that's a lot by, well, our standards. Okay. Now, the white dwarf that it's falling onto has a mass of about 1.35 solar masses. And critically, this is close to the upper limit that white dwarfs can handle. That's called the Chandrasekhar limit, around 1.4 solar masses. And white dwarfs cannot have any mass greater than this Chandrasekhar limit. And this is getting up close to it. And this is going to be important later because people are going to think that the white dwarf mass, well, after all, you have a white dwarf mass near the Chandrasekhar limit and you're piling matter on it at a ferocious rate. Well, the mass of the white dwarf should be increasing, right? And as it increases, it's going to not long from now get to the Chandrasekhar limit, and then the white dwarf can no longer last. Well, the idea would then be that the white dwarf, when it reaches the Chandrasekhar limit, it has to collapse, and people would think that this collapse is what causes the supernova of a particular type. So the distance of T Coronae away from us is about 3,000 light years. So we don't have to worry about it. We are outside the kill radius of T Coronae. In fact, if T Coronae became a type 1a supernova, we are still outside the kill radius for a type 1a supernova. It'll be a spectacular view in the sky, but it won't damage life on Earth. Okay, now I'd mentioned a little before that all novae have to recur. That is, that you have this cycle of accumulating matter on the surface of the white dwarf. It blows up, more matter accumulates. You have another nova eruption, accumulates more matter, and so on. Now, for most nova, the recurrence timescales are going to be thousands or even hundreds of thousands of years. But it's a continuum. And some nova have recurrence timescales of less than a century. It's a little bit of an arbitrary cutoff, but a century is convenient and traditional. And so a nova that has a recurrence timescale of under 100 years is called a recurrent nova. And these are by far the most important of all nova systems out there. But a recurrent nova is a subset of the larger class of nova. Now, recurrent nova are very rare because it takes very special conditions for them to have such a fast recurrence timescale. To get such a fast recurrence timescale, you must have the white dwarf mass greater than, something like 1¼ solar mass. It already has to be up near the Chandrasekhar limit, and you have to have a very high accretion rate. And the combination of those two circumstances is relatively rare in our own galaxy, or in any galaxy, actually. So there are only 10 known recurrent novae in our Milky Way galaxy. And there are about 10 known in the LMC, and I think a little, it's about a dozen that are known in the Andromeda galaxy. There aren't very many of them. Here's a list of them. T CrB is one of them. Fair enough. And for these eruptions, here for T Pix, there have been 7 known eruptions. There you go. And for IM Norma, there have been 2 known eruptions and 3 for CI Aquili. And down here for T CrB, there are 4. I've only told you about 2 of them so far. Well, okay, we'll get back to that in a moment. Well, what's happened here is there are 4 known T CrB eruptions, of which 2 have been discovered in the last year. And both of those are ones I've discovered. These are historical things, so I didn't make the observations, but I'm the one who made the realization that these old-time observations are of T CrB and are of a recurrent nova event. Fair enough. And so I have this green 2 over in here for the number of the eruptions on these recurrent nova that I personally have discovered. And I'm actually rather proud of these numbers. Here I've discovered 4 Scorpii eruptions, 1, 1, 4, 1, 2, 1, 1, 10 nova eruptions in all. I'm actually a little bit proud of that. I've spent vast amounts of time going back and combing through old historical literature, old archival plates, doing a variety of things, trying to discover this. And I've found 10 of them. Anyway, so this is what we have for type 1a. This is what we have for recurrent nova. Now, maybe the most important reason why recurrent novae are, by far and away the most important of all nova types, is because a lot of people think that recurrent novae are the way that you can solve the type 1a supernova progenitor problem. The question is, you have a type of supernova called a type 1a supernova. This is what the Supernova Cosmology Project used to prove the discovery of dark energy. And the question is, what type of a system makes for a type 1a supernova? This is one of these problems that back when I was in graduate school, people were arguing about, and they've been arguing about ever since. This is one of these problems. It's actually been elevated into being one of the grand challenge problems. I think there's large amounts of money if you can actually solve the problem. This is one of the grand challenge problems. And there are kind of 2 types of ideas for how the progenitor, what type of system can become a type 1a supernova. And so the community is kind of evenly divided between systems, which I'll call single degenerate, I'll explain that later, where basically it's T CrB. For this sort of for this half of this solution to this uber important problem, T CrB is the poster child. for single degenerates, most of the ideas have the progenitor passing through a recurrent nova stage immediately before you have the type 1a supernova, which makes T Coronae the prototype for a lot of people thinking that they have this solution to the problem. So the question is going to be, for all the recurrent nova and for T Coronae in particular, are they going to become type 1a supernova? And a lot of people think that they will. And for a lot of technical reasons, I disagree, but that's what we're trying to find out here. Okay, I pointed out that, that I had discovered 2 eruptions of T Coronae. There are now 4 of them that have actually been observed. And the first of my 2 went off just around Christmas in the year 1787. Whoa, holy cow. I have found the reports of this have appeared in an old, basically lost star catalog by an observer named Francis Wollaston. He's a fellow of the Royal Society. He was a big-time English, well, he was an amateur. Everyone back at the time, or almost everyone back at the time was an amateur. But he was kind of one level below John Herschel. In fact, he reported his weird observation off to Herschel, and here's a copy of the letter from 3 days after Christmas in the year 1787. His observation is best shown in his star catalog, where he gives an exact position. You see, what Wollaston was doing was he had selected randomly the constellation Coronae Borealis, and he was systematically making astrometry measurements of all the stars in Coronae Borealis. And in his catalog, he recorded the position of this unassuming star. And you know, the position that he records here is exactly identical to that of T Coronae. And there's no other star in the vicinity that he could have confused it for. And he has so he has something here that appears exactly at the position of T Coronae, and it couldn't have been an asteroid or a comet, because he observed this on 4 occasions, and he was getting astrometry on it on 4 occasions, and he would have detected any motion. Well, it can't be any other variable star, because there are no other variable stars in the area. It can't be a supernova, because a supernova in that direction that's only 200 years old or so would leave it would have been the brightest remnant in the sky, and Jansky would have discovered it back in the 1940s. Okay. So the only thing it could be is T Coronae itself. Now, Wollaston's limiting magnitude for the stars that he measured the astrometry on is about 7.8 magnitude. And so it has to be T Coronae. It has to be brighter than 7.8 magnitude. So T Coronae must have been in eruption around about Christmas time in the year 1787. There we go. That's the 3rd discovered eruption of T Coronae. Well, I found another one from the year 1217. That's 1217 AD. The report appears in a usual monastic annals of the time. This was written, these monastic annals typically had the learned man of the time going through and writing a summary of what happens each year. And for the year 1217, the abbot Burchard highlighted 2 things as happening as being the highlights of the year. One of them was this wonderful sign that was seen in Coronae Borealis. Well, he called it Ariadne's crown, but that's fine. This is written in Latin by Burchard, and he wrote it only a few years after this happened, and it appears in what's called the Erzberg Chronicles. And this is the chronicles of a monastery, which happens to be near Augsburg, Germany. Okay. So let me read you just the first little bit. In the autumn season, this is a translation, of course. In the autumn season of the same year, 1217 AD, in the early evening, a wonderful sign was seen in a certain star in the west. This star was located a little west of south in what astrologers call Ariadne's crown, which is Corona Borealis. As we ourselves observed, it was originally a faint star that for a time shone with a great light, then returned to its original faintness. Well, the duration of this transient in the sky is not well stated, but it can't be more than a month. And it's apparently, by the description, at least a week or something like that. Okay. Well, there are only three things that can go making for a transit in the sky that gets up to second magnitude or brighter, which is about what it would take for the Albert Burchard or anyone to have noted it with any care. There are only three things that can do that can make a transient that bright. One is a supernova, another is a comet, another is a nova. It has to be one of those three. Well, it can't be a supernova because there is no supernova remnant anywhere, even in the whole vicinity of Corona Borealis. And any supernova from about 800 years old would be incredibly bright as a remnant. And again, that would have been discovered long ago. It's not there, so it's not a supernova. Well, what about a comet? Well, if it's a comet, then, well, it can't be. Here's one reason. The reason it can't be a comet is because Burchard calls it a stella. He's reporting about a stella. And the medieval usage in Germany at the time was that the term stella means a point source star. He did not use any of the various German medieval terms for comet. So comets are distinct in their terminology from stella. Burchard was one of the most learned men of the time. He would not have made a mistake of calling a comet as being a stella. Okay. Let me give you a kind of a weirder reason why we know that Burchard's transient up in the sky could not have been a comet. Well, he calls it in particular a wonderful sign, mirabilis. And Burchard and other people of the time and place saved the word mirabilis for wonderful, positive omens. Mirabilis are the things that you talk about, biblical miracles, good omens. They're positive. Mirabilis is good, and he called this transient mirabilis. Well, why not a comet? Because comets in medieval Germany, in fact, medieval Europe, in fact, medieval in the world, in fact, all over the world, comets are always among the most evil, the worst omens up in the sky. In Burchard's writing, he talks about horrible things that happen in relation to other comets. Comets are always the death of the emperor, famines, the end of the earth, the fall of empires. Comets are bad. You would never call a comet mirabilis, but he did. It's not a comet. So to get a second magnitude or brighter transient, it has to be either a supernova, comet, or a nova. Well, it's not a supernova, it's comet, it has to be a nova. And there you go. You have a nova that gets this bright. And if it's any other nova than T Coronae, then we should have seen somewhere in that vicinity, we should have seen another nova remnant, and we don't. So the only possible case is it's T Coronae in eruption in 1217. There we go. Whoa. So we actually have a pretty good proof. I'll call it proof that T Coronae erupted round about October 1217 as seen by German monks. Okay, let me tell you some other work that I've done in the last on T Coronae that's been published in the last year. And this is a light curve of T Coronae. This is made from a fraction of a million observations. It starts with the Argelander observations back in 1855. And well, this particular drawing I made goes to, well, last year, which is when I published this. And the blue light is the blue dots are the light curve in blue band as taken from photographic plates or in modern times through a B band filter. And the green dots are for the visual observations, estimates made with the human eye looking up in the sky. And you can see what's going on here. You can see the 1866 eruption peaking up at second magnitude. You see the 1946 eruption, and I did not in this, for shame, I did not include Kamenchuk's observation at 1.7. But anyway, you see the eruption in here, and the secondary eruptions are hidden very closely in here. So they're all squished together when you have 150 years all put onto one plot. Okay, so you see that most of the time T Coronae is trucking along, at around 10th magnitude, maybe a little bit fainter. I'm going to call this the low state. So it trucks along. It's varying up and down. A lot of this is ellipsoidal variations I'll tell you about later. And it's also just random flickering. So here again, from, 1955 on to, 2015, you can see T Coronae trucking along at what I'll call the low state. But until someone had put all this together, you miss an important point here. And it's best seen in the blue light curve. For about 10 years before the eruption and about 10 years after the eruption, T Coronae is not in this low state. T Coronae is actually brighter by about 1.5 magnitudes. It's brighter. And so it trucks along at a plateau here. And well, here's the pre-eruption dip, which is what Leslie Peltier discovered just before the eruption. So we get a different picture of what's going on. And you can also see back in the visual data that T Coronae back in 1866 for the next decade also is in a high state before it transitioned back to a low state. Okay. So something's going on here. There's this high state both before and after the eruption, and superposed on it is this pre-eruption dip, and no one has any idea what's going on with any of these, okay? This is completely unprecedented, and there's no, at least published, theoretical model or even idea or schematic idea which explains what's going on. Okay, now, holy cow. Then things start hitting the fan. Back in the year 2015, Ulisse Munari, Dr. Munari, in Italy, recognized that T Coronae in the year 2015 was brightening. It was transitioning from its low state, and it goes to a high state. My cursor is not showing. Well, anyway, there we go. You can see around the year 2015 that T Coronae transitions from a low state, well, with a blue magnitude about 11.5, and it goes up to about 10.5. It went from a low state up to the high state. This is just exactly what happened back in 1935. And we see that T Coronae is behaving from eruption to eruption, wherever we can check it. It's behaving identically. So if we see a transition from a low state to a high state, it is a harbinger. It's pointing that there's going to be an upcoming eruption. Ha, there we go. And roughly, we know from the 1935 high state that the eruption is going to happen, a little over 10 years later. And so we can go 10 years after the start of 2015, and we're getting around 2025 for an eruption. The eruption is coming soon. Okay, let me show another thing that you can go getting from this light curve. You can find the ellipsoidal variations. So the ellipsoidal modulations here are where you have T Coronae is going up and down, up and down, up and down. It's a little chaotic. T Coronae has a variety of variability of which the superposed on top of the ellipsoidal modulation. Here's a time period of 4 years, and you can see T Coronae going up and down. Now, this has to be from what we would call ellipsoidal modulation, where you have the gravity from the white dwarf is pulling the red giant out of round into a shape much like an American football, with the point of the football always pointing towards the white dwarf. Okay. And so as the red giant goes round and round the white dwarf, sometimes you see this out of round star side on, where you have a lot of surface area and the star appears relatively bright. Sometimes you see it point on, in which case you have a relatively small area that you're seeing and the star appears fairly faint. So the star appears faint at the times of conjunction. So here you have a conjunction of T Coronae, and this allows us to know the orbital phase, the rotational phase of the orbit, well, from the light curve. And you see, I can track these ellipsoidal modulations going back even to 1866. In fact, that's the reason why I made that long light curve. I was trying to track it back in time. Okay, so you can track these ellipsoidal modulations going back to 1866. And you can put it together in what is called an O minus C curve. I'll tell you in words what this all means. What you have is from 1867 to 1946, but that interruption period, there was no large period change. But in the year 1946, consistent with the eruption, there was a large period change in the orbit. The period changed suddenly, and it changed suddenly by a huge amount. And that huge amount, well, we don't understand that. That's yet another thing which we don't understand about T Coronae. How can the orbital period change because of the nova eruption by this amount? Well, I don't know. Okay, and then from 1946 to 2022, well, actually, I've done this up until recently, so it's up until now. There is a parabola in this curve, and that means that the steady orbital period is changing over time. And it's changing incredibly fast. The time scale for the change is 70,000 years. And that's incredibly fast for the evolution of a star. So here we have a mystery. We don't really understand how T Coronae can possibly have these high period changes. Okay, let me go back to a point I've raised before, and that is that T Coronae is going to erupt soon. Well, the basic thing that many people realized was that if T Coronae goes off in 1866 and if T Coronae goes off in 1946, that's an 80-year interval of an 80-year recurrence time scale. And so even back one day after the 1946 eruption, Lindley, that guy from the BAA, was already predicting that round about the year 2026, there will be yet another eruption. So 80 years after 1946 is going to be around 2026. And so we can expect, well, sometime around now, another eruption. Now, I did this exact same calculation back when I was in high school, which shows you that many people made the same calculation. We can do a better version now because now we have more eruptions, and so we can get some fine tuning on the inter-eruption intervals. We have 4 observed eruptions here, and we can look at the time intervals between them, and it goes from, well, 81.4 years on average, 500 years ago, and it's getting shorter and shorter, okay? And so now it's at 79.7 was the time between then and then. Okay, fair enough. If you take this as any sort of a linear progression, which it almost has to be, then that means that the next interruption time will be, well, it turns out 78.6 years apart, which puts us down to the year 2024.7, which is a couple months from now. Now, this is pretty crude, got to admit, but there are better ways of trying to fine-tune the fine-tune the date of the upcoming eruption. One of them is to note that the high state started in 2015, and if you have the high state now behaving the same as it did before the 1946 eruption, well, you can look at the time intervals, and that's going to occur, well, round about the year 2025, the middle of the year 2025, with an uncertainty of a bit more than a year. Let me show you a little bit how this is done. Here, this is a light curve plot. The green are for visual light. This is all visual observers contributing. Much of the scatter is due to the ellipsoidal modulation, which is not well resolved here. And much of the scatter is also due to T Coronae flickering up and down. Okay. The blue dots are the B band. Well, in this case, it's all CCD photometry by the amateurs the world over. Okay. So this is the light curve as seen up until actually yesterday, all averaged together. There are a gazillion points in here. So this is time averaged into 1/100th of a year time bins. Now, also superposed on here is that purple curve. And the purple curve is the blue band light curve from 1946, just simply shifted in time, okay? And so you can see the sharp peak that goes up to, well, way up above. That's the primary eruption. Here's the secondary eruption, and here's the high state, the pre-eruption high state. Here's the post-eruption high state, and here's the pre-eruption dip, which we're now in. So if you look at the times of the rise of the start of the high state, and you shift this, what it did back in the 1940s, if you shift that light curve back and forth, you can read off what the eruption date should be. And that's where you get the middle of the year 2025. Now, you can do a little bit better because starting in April of last year, the pre-eruption dip started. And you can see that here, the blue band light curve, it suddenly starts fading. And we've been in the bottom of this fade for a few months now, okay? And well, back in 1946, this pre-eruption fade happened about 1.1 years after the start. The eruption happened 1.1 years after the start of the fade. And you can look at this and make the prediction 1.1 years after the start of the pre-eruption dip in April 2023 comes out to be, oh, well, let's call it May of this year. No, there's uncertainty here because, well, we already see that the pre-eruption high state was a little bit different. It was a little bit higher back in the 1940s than it has been in the last decade. And this is we don't know, might changing the timing of this. So this is, this 2024.4 prediction is made assuming that the behavior this year is the same as it was back in 1946, which is probably pretty good, but it means there's going to be rough edges. There could be larger uncertainty than expressed here. So what you have here is that the expected date of the upcoming eruption is going to be, well, about a month ago, but there's a large uncertainty of more than a quarter of a year, let's call it 3-4 months. And so we're still roughly in the middle of the expected time. So T Coronae could go off any night now. It could be going up. And in fact, T Coronae has probably not gone up in the last 15 minutes. I'll tell you why in a moment or two. But T Coronae could go up tonight. T Coronae could go up, well, any month now. And it really almost has to go up sometime before the end of the year. But there's substantial uncertainty in knowing exactly the date of the upcoming eruption, but it's any night now. Well, let me show you a blow-up of the recent AAVSO collected from worldwide amateurs. This is the light curve of T Coronae. So we have the blue observations, the B band. Here are the visual observations. Here's the R, the R-band observations, and here's the I. These are progressively blue, green, well, red, and far red. We also have down here, these ellipses show ultraviolet observations. Okay, so this is actually an awesome record. The amateurs are coming up with a wow record. The small telescope users of the world are coming up and doing something that professional astronomers can't do. No professional can get enough telescope time to get this coverage. And so this is entirely on the amateurs of the world. And they've been stepping up like mad. So what you have here, but by the way, again, this plot is up to, I think, 2 days ago. And so what you have here is a record. You can see the ellipsoidal modulations. There's a peak, a peak, a peak, a peak. These are periodic. You can see these ellipsoidal modulations, and you can also see that now the T Coronae is substantially fainter than it was, well, even back, well, before the pre-eruption dip started. Okay, so this is the pre-eruption dip in here. Fair enough. And it's kind of awesome what the world's amateurs are doing. Currently, and actually for the last 2 years, the small telescope workers of the world are coming up and monitoring T Coronae with an average of every 6 minutes. So on average, every 6 minutes, somebody out there in the world is looking up to see whether T Coronae has gone up. There's a lot of merit and prestige and science importance for catching T Coronae on the rise. You want to catch T Coronae very fast because when it goes up, the eruption is up and down, and it's in a day or two, and so you need fast notice to the world. The world needs fast notice. So people, astronomers, wherever, can turn their telescopes and start looking at it and start making measurements. So there's high utility in getting a fast eruption. And there's high prestige in getting a fast eruption. And the rise is very fast. So presumably some observer, once every 6 minutes, will be able to say, hey, that star is brighter than it should be. Well, I'm gonna phone home. There you go. Okay. Now, here's something special for the people of the Philippines. You know, T Coronae is an incredibly fast rise. So what happens if the rise happens when T Coronae is above the Pacific Ocean? There aren't very many observers around the Pacific Ocean. And so that's a little bit of a nightmare for me, is what happens if T Coronae rises when it's, well, over the Pacific Ocean, and maybe no one is looking, or the observations will be sparse. And it'll be a while before anyone could confirm the discovery. So all of a sudden, the Philippines are perfectly set up to catch the T Coronae eruption just as it's coming out from this gap in the Pacific Ocean. So it could well be that T Coronae goes up in this Pacific Ocean gap, and that the first people to catch the eruption of T Coronae is going to be someone in the Philippines. So if you're in the Philippines, you should check T Coronae. It's in the evening sky right now. You should check it every time, every clear evening, just after it gets dark. You might have the discovery. Well, when T Coronae goes up, there's a lot of science, and basically most professional telescopes will be turned towards T Coronae. Here's a listing of them. There are many. And of course, you're going to have a gazillion small telescope users are going to be going off and watching it. Here's one you might not have thought of: neutrinos. It turns out that theoretical predictions suggest that T Cor should be emitting enough neutrinos that it will be detectable here on Earth with currently operating neutrino detectors. Who would have thought? And so the neutrino detectors of the world are on high alert. So they know it's coming. They're parsing their data in the optimal ways. And it's possible, we don't know, that's why we look, this is science, you don't know what the answer is, so you look to see what reality is. We don't know, maybe T Cor will be discoverable by neutrino detectors. Whoa, be awesome if it is. A lot of fun. Okay, so what do we hope to get out of this upcoming eruption? Well, one thing we hope to get is just simply having people, you, me, us, just looking up and seeing this thing up in the sky and pondering our place in the universe. But there are science mysteries that will hopefully be solved with the upcoming eruption. So there are some T Cor specific mysteries, and I've already been mentioning things that we don't know about them. We don't know what the high states on either side of the eruption are. We have no idea. This pre-eruption dip that Leslie Peltier discovered. What is it? Who knows? And there's also that unique secondary eruption that happens about half a year after the primary eruption. Again, no idea. Okay, so those are three things that I hope will get discovered. Mysteries solved. Here you have T Cor doing utterly unique things, and maybe we'll actually be able to solve what's going on. Well, for each of the three things, work over the last half year has provided ideas and possible answers for them. Okay, for the nature of the unique high states, I claim, this is unpublished, I claim that the unique high state is just a normal symbiotic nova eruption. Many of those are seen in a different setting, but I think it's just a symbiotic nova eruption involving hydrogen burning on the surface of the white dwarf. Okay, fine. Within this idea, I have the trouble, which I have no good answer for, explaining the timing of the high states. Why would you have a high state for a decade before and a decade after, starting and stopping as it did from eruption cycle to eruption cycle? I don't have a good answer. There we go. For the nature of the pre-eruption dip, well, this is again unpublished, but it's obvious from the spectroscopy that have been obtained by the amateurs. The amateurs around the world have been monitoring T Cor wonderfully, and they have provided an answer for the pre-eruption dip. The pre-eruption dip is not any shell of dust hiding the underlying star. No, the pre-eruption dip is simply the end of the high state. And so that's actually a pretty sure answer. Now, it doesn't explain why the high state ended, but there you go. We at least understand what the pre-eruption dip is. For the nature of the unique secondary eruption that happens a year after the primary eruption, Dr. Munari in Italy, he has actually published this claim already, just a couple months ago. He's published the idea that the secondary eruption is actually caused by irradiation from the hot white dwarf heating up the inner surface of the red giant, which as it rotates through the field of view, we see the hot surface of the red giant, which is going to be bright, and it then rotates out of the field of view and the hot source fades. It could be, it really could be. But for this to be agreed and accepted, it has to provide, it has to be tested with the upcoming light curve. That is, Munari makes a very particular prediction as to when this secondary eruption will happen. And if he's wrong, the phasing of the secondary eruption will be by some other reason. But if the peak of the eruption happens at exactly the right phase, then Munari's claim will become quite reasonable and probably will be accepted. Anyway, so the hope is that the upcoming T Cor eruption will provide us answers to many of the mysteries relating to T Coronae itself. But you know, I'd already alluded it to earlier. T Coronae is the prototype, the poster child for one whole class of progenitor models for type 1a supernova. Remember, identifying the progenitors of type 1a supernova, this is one of the most important questions in modern astrophysics. This is a question which is elevated to a grand challenge question. Okay, so the question is, what type of star produces a type 1a supernova? And there are two broad classes of models. One is a single degenerate, so-called, and it's called a single degenerate because you have only one white dwarf in it. A white dwarf is a degenerate star, so you have only one white dwarf. And it consists of a normal star accreting onto a white dwarf. You have only one white dwarf, so it's single degenerate. And you have matter accreting onto the white dwarf, which the mass of the white dwarf gets larger and larger until it hits the Chandrasekhar mass, when it will or might explode as a type 1a supernova. That's the whole class of single degenerate models. And T Coronae is the poster child for this class. The competing model is the double degenerate. Double degenerate, that means there are two white dwarfs. In fact, two white dwarfs in very close binary orbit around each other. And by ordinary gravitational radiation, the two stars are going to in-spiral on each other. And towards the end, they're going to be in-spiraling so fast that it's almost a head-on collision. And you end up with a merged two white dwarfs. And the pair of white dwarfs is over the Chandrasekhar limit. And all of a sudden, the thing has to collapse. And the collapse is going to cause rabid nuclear burning. And the nuclear burning is then provides enough energy that it blows the star to kingdom come. And there you go. So you have these two competing classes of progenitor models for type 1a supernovae, of which T Coronae is the poster child for one of the classes. So the question is whether T Coronae is going to become a type 1a supernova. Now, in this single degenerate picture, it's actually relatively hard for these systems to become a type 1a supernova. There are two requirements that have to be made. One is that the mass of the white dwarf has to be increasing so it can get up close to the Chandrasekhar mass. Well, you're feeding mass onto it at a rapid rate in T Coronae, but you're also ejecting large amounts of mass. So the question is the white dwarf in this system and in T Coronae, is it accreting more matter than it's blowing off, or is it blowing off more matter than it's accreting? Turns out that's a hard question. We actually have a pretty good estimate of how much matter is accumulating onto the surface, but it's hard to measure with any exactitude how much mass gets blown off. And I don't see a way for the upcoming eruption, I don't see a way at which we can actually end up doing that, or not to the accuracy needed. So that's not going to help us, I think. But there's another requirement, the nature of the white dwarf. You see, for that white dwarf to ultimately blow up as a type 1a supernova, it takes an awful lot of energy. And it turns out the only way you can get that energy is nuclear burning, fusion of the carbon. Only carbon produces you enough energy per nucleon per nuclei. Only carbon produces enough energy to blow up this star to kingdom come. Okay, so it turns out there are multiple types of white dwarfs. The most common is a carbon-oxygen white dwarf. That's going to be like what our sun is going to turn into. A carbon-oxygen white dwarf, if it's pushed to the Chandrasekhar limit, it'll collapse, and you have a lot of carbon, and it's going to burn, and you're going to have enough energy to blow up the star. So a carbon-oxygen white dwarf can blow up as a type 1a supernova. But you see, there are other types of white dwarfs. In most particular, there also can be a white dwarf that is made up mostly of oxygen and neon. And when that reaches a Chandrasekhar mass, it's going to collapse but you won't have enough nuclear burning energy from burning carbon. It's not going to be able to, it'll fizzle. It won't be able to blow the star apart. You're going to have an accretion-induced collapse. It's just going to collapse down to a black hole, and you're never going to get a nova eruption or a supernova eruption from it. So if T Coronae has an oxygen neon white dwarf, it's not going to become a type 1a supernova. If T Coronae has a carbon-oxygen white dwarf, well, it can become a type 1a supernova. So which is it? Does T Coronae have an oxygen neon white dwarf? Well, it's hard to tell because a lot of the mass is hidden down below the bottom where inside the white dwarf where we can't see it well. But during a nova eruption, it blows off a lot of the mass from the surface. And the mass that blows off from the surface might or might not contain large amounts of neon. Well, if it's a carbon-oxygen white dwarf, there's no way you can get much neon floating around, so you don't get much neon in the ejecta that you can see. However, if it's an oxygen neon white dwarf, you have scads of neon near the surface, and it gets blown off as part of the ejecta. And looking at the gas shell around the nova, you'll be able to see a large amount of neon. So it turns out that around 20% of known novae are neon nova. Okay. And in fact, you can get very high abundances of neon. One of them, or actually several of them, have neon. The neon in the gas is the majority of the gas. Whoa, where'd that come from? You have a good neon sign there. So the question is whether T Coronae is going to become a neon nova. It turns out that's a hard thing to detect, actually. You can only see the neon lines late in the light curve and only, or primarily, when you go looking far in or relatively over into the ultraviolet light. There's a pair of neon lines at 3,800 angstroms, which should be very bright and prominent for about a month towards the end of the eruption. Now, I think I actually know what the answer is on this, because there was a French observer back in the 1946 eruption who happened to take a spectrum at the right time and going sufficiently far into ultraviolet. We only have this one spectrum, but it shows really bright neon lines. Now, most modern folk would say, oh, that's old data. We can't believe that. Go away. Oh. Or a better way of putting that is, yeah, let's see it again in a couple months. So I think I know the answer. T Coronae is a neon nova, but it'll be convincing only when we see it in the upcoming eruption. So if T Coronae turns out to be a neon nova, then T Coronae cannot become a type 1a supernova. And there you've just shot down the poster child for the single degenerate model. The single degenerate model kind of goes away. Well, it'll never go away, but basically it'll be refuted in most cases. You always have people holding out, but whatever. So if T Coronae is a neon nova, that question goes into one of the big grand challenge, one of the current most important problems in astronomy, all for T Coronae. Okay, so those are the mysteries I want to have solved. But you know, the thing I really want to see is I want to see T Coronae up in the sky as one of the brightest stars in the sky. You know, when you look up at it, it's going to be, well, it's not going to be exciting, but it'll be intellectually exciting. You'll be able to see, kind of see our place in the universe. You'll be able to see a star blowing itself up, and there you go. You'll see the hellfire in the sky above your head. So why didn't I stop there?
Thank you. Thank you so much, Professor. Wow, that was a very, very educational and exciting presentation. And we are now excited here in the Philippines to bring out our telescopes and
You people in the Philippines, you guys have the wonderful case. You're at the edge of the Pacific Gap. You can go off. You might be the discoverer of T CrB.
So let me start with in the Q&A. Maybe one of the first questions that I would like to ask here is for our amateur astronomers, who with their backyard telescopes and cameras, how can they help in the observation and contributing to the scientific
Sure.
information on T CrB?
In particular for T CrB, one of the things that I find useful is actually just ordinary visual observations. It's going to be amateurs that define the light curve. So even in quiescence, those visual magnitudes are important. That's what I'm driving everything off of. You need consistency with going back to 1867. So just ordinary visual observation. This is AAVSO sort of stuff. You get a finder chart with magnitudes nearby compared. You look at it through your telescope, you determine the magnitude, and you report it. That is incredibly wonderful. During the eruption itself, using binoculars or your unaided eye, getting magnitudes, the function of time, that's something that is important. Again, the professionals aren't going to be getting this. Just simply reporting magnitudes that you see is vital and important. But for T CrB in particular, for people in the Philippines in particular, just simply looking for T CrB in eruption, that is our best solution to this Pacific Gap.
Wow.
There we go.
Nice. So there's another question here from Kenneth Harrison. Can one sign up for a timely text warning or something similar, warning of its eruption? Yeah, is there a monitoring site? Yeah.
That would be that's important because T CrB is up and down so fast that if you get the notice a day late, everything's well, it's not all over, but the peak is long gone. So what I do is I've signed up on the American Association of Variable Star Observers, and the discovery report will get there very quickly. And as the discovery report gets there very quickly, it then gets passed around the world within minutes. And so I can tell you T CrB has not gone off within the last 15 minutes because my email is not buzzing with, holy cow, it's been discovered. So T CrB has not gone off in the last 15 minutes. So the way I do it is I go to the AAVSO. There's a way you can have it. It's kind of nitpicky deep down in, but you can have it notify you of when T CrB is seen to be above some threshold. Presumably an eruption. Sometimes there are just false alarms. You got to live with that. We're operating on a hair trigger, so you're going to get false alarms. This AAVSO website is the only place I know of where you can get notification pushed out to you. There are a variety of websites run by, for example, the what were the IAU circular people, the CBATs, where things will come out. It'll come out in the ATELs instantly, and so there are a variety of places. But the only way I know of to get notifications pushed to you is by going to the AAVSO website. But at some level, presumably the news outlets will hear about this, and they presumably will publish the announcement immediately. And so maybe with a half-day notice, just simply keeping your ears attuned to media outlets, you'll be able to hear the eruption announcement.
Thank you.
So I have no perfect or good solution.
Thank you. This is a question from Andy Gingel. In connection, this is connected with the observation. How long will it take for the eruption to get from the start to its brightest magnitude? So
We don't know.
yeah.
We know from the Schmidt observation that it brightened by 3 magnitudes in a couple hours, and then it faded by 1.4 magnitudes in a few hours. So presumably going from ordinary quiescent level up to the peak, probably a few hours. It could be minutes, but probably a couple of hours. It's fast. It's really fast.
Thank you. This is from Laure Champagne Aslan. How can an erupted nova shine for a long time?
Well, the century-long in quiescence, that's not the nova eruption. What we're seeing is the SAR. We're seeing the red giant in the red, and in the blue we're seeing the accretion disk, and they're just sitting there trucking away. So the nova eruption itself lasts 30 days, something like that. And that's the time it takes for the ejecta shell to keep expanding out, thinning as it goes, cooling as it goes. And at some point, it just thins and cools till it's unobservable. And all you can see then is the underlying binary star.
Thank you. This question is from Dante de Jesus. Does T Coronae produce gravitational waves?
Yes, it does. They are not observable. That's actually a wonderfully good idea, but the answer definitely is for sure no. Part of the trouble is that gravitational radiation is produced by the binary orbit, where you have a gravitational quadrupole rotating around, but the orbital period is 227 days, and that makes for a frequency for detection, which even LISA can't find, and LIGO and so on has no chance in the world. So no, T Coronae will not be visible in gravitational waves.
Yeah,
nice idea.
In connection with this, what happens to the magnetic fields of red giant and white dwarf during eruption?
Well, I don't know. We don't even know for sure that there are magnetic fields. Presumably the magnetic fields, whatever they are on the white dwarf, if there are any, will be entrained to the exploding matter, which will carry some of the magnetic field away, not all of it. And after it gets carried away, the white dwarf will just go back to whatever it was before. And the magnetic fields in all these cases must be sufficiently weak that it's not going to affect any dynamics or anything at all. So there might be magnetic fields in the system, but it doesn't matter, and we won't be able to observe it.
Thank you. I think I've read all the questions in the Q&A. Can I ask the panelists if they have questions? Edwin?
So for the panelists, when's the last time you went out and checked to see whether T Coronae is erupting?
Well, one of us took a picture the other day of T Coronae. I think 2 pictures, 2 images. But
was it bright?
Most of the it's very faint. Peter, can you answer?
Yeah, hi, Brad. And that was a wonderful, wonderful talk you gave. So just the other night, I was able to observe and image T Coronae using the smartphone on a telescope. But comparing it with last month's observation I did, there was a distinction in brightness. It's actually brighter last August 12 than the one in July 5. So
Right, that's that light curve I showed.
Yeah. Yeah. So it still was exciting because it's already showing like signs that it's getting brighter as the nights go by, and it's really way up high, around 7:30 p.m. Really quite high. So we're really fortunate that we'll have the hopefully we have the chance to see it when it erupts.
Yeah, so T Coronae is now an evening object, and in a few months it's going to be getting closer to the horizon at the end of dusk. And but T Coronae, even from the latitude of the Philippines, will always be visible all throughout the year, even if you have to look. Well, you'll have to be looking fairly low on the horizon, but it'll always be up there. You'll always be able to catch it during dark sky to check it out.
So I'm just curious. So based on the previous records that we have, um, how many times would the blaze star erupt before it fades away, or do we have any history that it has like weakened from the previous years?
No, we don't have information because the old photometry, well, the pre-1866 photometry is not accurate. And the 1866 and 1946 photometry shows to within error bars that the light curves are identical. So it doesn't look like the eruptions are fading. And probably the peak of the eruptions are being thermostated by conditions on the white dwarf. And so that shouldn't change over time. But you know, things that are worrisome for a theorist is there are some things that are changing fast on timescales for stellar evolution. I showed you the light curve showing how the orbital period is decaying, getting smaller at a rate which is not understandable. We don't know why it's fading. The timescales, the evolutionary timescales, there are 70,000 years I quoted. And if you look at I also showed how the time between eruptions is apparently speeding up. Okay, fair enough. If it's speeding up, then it's doing so on a time scale, and a simple dumb linear extrapolation would have it down to 0 recurrence time scale in 14,000 years. And so here we have time scales for T Coronae changing on the time scale of thousands of years. And there's no way of understanding, or that I know of anyway, there's no way of understanding how T Coronae could be evolving so fast. So maybe your question about the peak brightness, whether it's the peak brightness of the nova peak, whether it's fading, well, maybe we should revisit that after this upcoming eruption to see whether it actually is different than it was back in 1866.
Thank you very much, Brad.
So, Brad, first of all, we would like to thank you so much for a very, very wonderful presentation. Yeah, we really learned a lot about T Coronae. Thanks to you. Now, as I had mentioned in my introduction, you are very good with detective work, and you showed that today by being able to dig up observations dating back to the 13th century. Thank you. And we remember the excitement, all this waiting for T Coronae to erupt. We remember the excitement that in 1987, when the supernova erupted in the Large Magellanic Cloud, everybody went crazy. All the observatories and observers were looking at the new supernova. So now I just wanted to put things in perspective that we're all waiting for this nova to erupt, but actually we are going to look at an event that happened 3,000 years ago, correct? So So anyway, my question is, Melda and I are just curious, what is your actual observing plan when T Coronae does erupt? What telescope are you going to use? Do you have reserve time on Hubble or James Webb? What's your plan?
I have intentionally not tried to put in targets of opportunity. In particular, I have been much more being a cheerleader and a godfather for other people doing the work. Part of the trouble is it takes, there are so many satellites and so many telescopes and so many ways of observing it. I can't do any more than one. And it turns out that for the people to do it well, for example, all the time I've had down in Cerro Tololo doesn't work because, well, T Coronae is up in the north. So I have been more as a co-eye and prodding people to put in their targets of opportunity. For example, Mike Schar is going off and looking for light echoes around it with HST. And so I haven't been involved in that. And also I've been heavily pushing for amateurs to go off and get the observations. For example, in particular, of the neon lines late in the light curve. This is something that amateurs can do, and the professionals, I shouldn't say won't, but they can't do as good a job as the amateurs. And so I think that's one of the critical points here is what are these what is the spectroscopy showing of T Coronae late in the eruption? I'm not a spectroscopist, so I am more as a cheerleader and someone who encourages and eggs on people to make the observations. For what it's worth, there are some points where actually quite good information can be gotten just simply by certainly knowing the eruption date. And so I already have that paper written. All I have to do is put in the correct eruption date, update who discovered it, and then repeat the calculations, which I've already done, correctly with the correct eruption date. And so I have the paper already written, and it can be submitted to ATEL within an hour of the eruption.
It's just a matter of filling the blanks, filling in the blanks.
I've already done the calculations, and so I'd have to update the calculations for the correct eruption date, but there you go.
Brad, the exciting part about this is you can predict basically a time frame when this is going to happen. There is still a lot to learn, and that we can learn from the eruption. Now, amateurs can monitor it visually, do spectroscopy, do photometry for the light curve. But are there, the professional astronomers have telescope times all over the world. Is there a consortium or whatever that, or a decision that if this erupts, we only have this much time to observe, we're going to, take your telescope time away and
quite right. There is no large consortium. This is all being done by individual astronomers who are the people with the Chara telescope have long been aware of this. They have already put in their target of opportunity observations so that when T Coronae goes up, Chara just basically immediately turns around and looks. Okay, and it will keep looking throughout the eruption. Same thing with Hubble Space Telescope. There, the lead time is longer, but the target of opportunity proposals are already in there. And so when T Coronae goes up, Chara will initiate his target of opportunity, and HST will go over and look. It'll take about HST about a week to get over, but for the science, that's actually perfectly fine. Because you got a little bit of trouble here. T Coronae at peak is going to be so bright, it's going to be hard to, it's going to saturate detectors of many of these telescopes. So looking at it with the Keck telescope, well, you might not want to actually. An amateur's telescope can get actually just as good signal to noise and just as good spectral resolution as can the Keck. And the Keck people will have a hard time with the saturation. So yes, for the last year now, observers on basically all the telescopes that you can get unique stuff on have already put these targets of opportunity in place, and they'll be invoked as soon as the amateur comes in and says, it's up.
Yeah. Well, Brad, also you're talking about people in the Philippines because of the gaps in the Pacific. But remember, you also have people in Japan, Hawaii. And
you got to beat them. You got to beat them.
Yeah. And I was telling Edwin,
I actually got an email from this morning from Mike Linault. So Mike Linault is he's discovered previous recurrent nova eruptions on his own. And he is a frequent monitor of recurrent nova eruptions. And he lives in Hawaii. Okay. So yesterday I sent an email basically telling him also about this Pacific gap. He knows it perfectly well. And that he in Hawaii should be monitoring T CrB every hour on the hour. And the email this morning came back and said, oh, gee, yeah, I live in Hilo, or live in Volcano. That's where Steve O'Mara used to live.
Yes,
I live in Volcano, and we get frequent fogs, and I might not be able to observe as frequently as I can. And he doesn't know who else on Hawaii could look. So maybe Hawaii filling the Pacific gap might not be perfect. And anyway, there's a huge gap between Hawaii and the Philippines.
And also, Brad, Atlantic. Other than you have, observers in Iceland and Greenland. So and the Nova Scotia area. And I told Edwin, hey, we're on the East Coast. So.
No, I don't know of any Icelandic observers who've been monitoring this, and nor Greenlanders. So probably the best try to fill the Atlantic gap is that people in Europe or England or Spain can, and they have been, observing T CrB as late in their night as possible, with T CrB getting lower and lower. And then the observers on the American East Coast picking it up as soon as it comes into, as soon as it gets dark. And that will close a lot of the Atlantic gap. And so I do know that Barbara Harris and Sean Dvorak are well on top of this. And they're the discoverers of the of the U Scorpii eruption. And so Barbara Harris and Sean Dvorak are the best hopes for doing the Philippines on the Atlantic.
Great. Thank you so much.
Wonderful.
There's another question here. It has something to do with the historical account, the German historical account in 2017, from Owen Gwyn. He's asking, the 1217 record says this star was located a little west of south, but would it have been very much west rather than west of south? Might it have been another star? If it would have been very much west rather than west of south, might it have been another star?
That part of the passage is confused because we don't really know what they meant when they said west and south, and we don't know by how much. But they are pointing to Ariadne's crown, which is Corona Borealis. So it can't be too far away from Corona Borealis. And so you can ask the question whether there's any supernova remnant anywhere in the vague vicinity of Corona Borealis, and the answer is no. And is there any other nova that could get up to second magnitude anywhere in the vicinity of Corona Borealis or neighboring constellations? And the answer is no. The only old nova that is anywhere in that vague vicinity that could possibly get up to second magnitude is T CrB.
Any other questions from the panelists before we let Professor go?
Yeah, I just want to say something, Brad, that I noticed while you were giving the talk and you're doing your detective work, because I think we should, all of us should do this. Any observation that we do, it's important that, maybe somebody could start up a depository of a repository of information. You are very lucky you had access, because recently we lost a friend who has a lot of old books with a lot of information, and it got kind of some were sold, some were
Dispersed.
it got dispersed. And so the thing is, this is Owen.
Professor Owen Gingrich, you know him very well.
Very
Yeah.
well, right? So I was just telling Edwin while you were giving the talk, imagine all the data that were in the collection of Owen. Historical collection of books. So
Manuscripts.
and manuscripts. So I wish they all went to a central repository of
Actually, they did. Owen Gingrich's collection, with a few exceptions, was donated to the Harvard libraries, and they are now available at Harvard. I would come back and say, when you try and get in to see them, Harvard has, it's not easy to get to see anything in the Harvard collections, but they are there and they are available. So they have indeed almost all gone to a very particular venue, and that's the Harvard libraries.
Oh, is it the Holter? Is it the Holter?
Effectively, yeah. It's not quite, but yes.
Brad, speaking of Harvard, have you or somebody else checked the Harvard glass plates for any photos of T Coronae in the past?
Oh, I've done it multiple times, you bet.
Oh, you did?
Yes. I have examined every one of about 5,000 plates, and yes. So in fact, most of that blue light curve that I showed, that there was that big 1855 to current day light curve. Other than the points in the last 20 years made with amateur CCDs, all of the rest of them are with blue plates, almost all from Harvard.
Wow. Okay.
Yeah. So okay, we're talking about Owen's collection there, but how about the observers from Europe and all that? I mean, they're not sending it to Harvard or.
Yeah, that's a catch can thing. Looking for the old observers, Julius Schmidt, for example. For many of the old observers, you have to go to particular archives which have saved their papers. And so I've gone to the old Royal Astronomical Society archives and the BAA, and there are a variety of archives where their original observing logbooks are located, and I've been off using those for T Coronae quite heavily. One of the things that is annoying for me is that the original logbooks of the Reverend Francis Wollaston, remember he's the observer, the observer or discover, well, he didn't realize what he saw. The observer for the 1787 eruption, I have not been able to find any place where his logbooks are still extant. Maybe they were just tossed. There we go. So for European observers, actually for American observers too, it's really catch can as for what gets saved. So one of the things I've been trying to do is in all my publications on the T Coronae and other stars, actually, I've been very careful to record my modern analysis of every last old observation, even if I don't show the logbook that I got it out of. The data, the information is still there.
Great. Thank you so much, Brad.
Thank you. There's another question here in the Q&A. I think this is the last question. Brad, from Jack Martin, the question is, Brad, have you revised your eruption time window?
No, the best estimate still is 2024.4 plus or minus 0.3. We're a little more than halfway through that Gaussian-shaped probability interval. So it hasn't happened in the first part of the T Coronae has not erupted in the first part of the of this eruption interval, but it's going to occur. Well, so the eruption must be in the last part of the eruption interval. So that would put the most likely time, given what the lack of eruption in the last couple months, that would put the best time, the most likely time for it erupting would be, well, tonight. But if it erupts anytime in the next few months, or anytime actually even before the end of the year, then it's still fully consistent with with our best predictions to date.
Thank you. So thank you again so much for your patience in answering all the questions. And you've really infected a lot of us here in the Philippines with the enthusiasm for trying to observe this phenomena. So before we close, we would kindly allow us to present our ALP Certificate of Appreciation for this magnificent talk. And it reads, this certificate is presented to Bradley Elliott Schaefer, Ph.D., for the webinar entitled The Brightest Nova in Generations Coming Soon to Your Backyard, held as part of the ALP Astronomy Expert Speaker Series of 2024, given the 70th day of August, 2024, signed by Mr. James Kevin T, President, and Dr. Jose Aguilar, Vice President. Thank you very much again. And
well, thank you for the
wow,
certificate.
it was a long talk, but I didn't feel that it was long. Great. Thank you. Edwin, Dada?
Are you announcing the
Yeah.
future speakers?
So, okay, let me continue. So before we conclude today's webinar, I would like to thank all our attendees, and there are a lot of them, for patiently being with us for the entire talk. And we will be sending your certificate of attendance by email to all registrants who were able to join us. And by the way, this is the 24th webinar in our Astronomy Expert Speaker Series since we started 2 years ago. Our first speaker was the late Dr. J. Pasakov on April 23, 2022. Our other esteemed speakers were Mr. Zolt Livey, Mr. Joe Rayo, Mr. Fred Espenac, Mr. Robert Reeves, Mr. Ken Crawford, Mr. Dave Eicher, Professor Matthew Barlow, Mr. Scott Roberts, Father Christopher Corbally, Mr. David Levy, Mr. J. Kelly Beatty, of course, Imelda Joson and Edwin Aguirre, Dr. Daniel Green, Dr. Heidi Hamel, Dr. Deborah Emel Green, Brother Robert McKay, Brother Guy Consolmano, Miss Hilary Andales, Dr. Valentin Pillay, Mr. Wally Pochorka, Dr. Robert Nemiroff, Dr. Michelle E. Brown, Dr. Jonathan McDowell, and for today, of course, Dr. Brad Schaefer. We are so grateful for all our webinar speakers who have very generously gave their precious time to share their knowledge and expertise to the world astronomical community, and we can never thank you enough. For those who missed our previous ALP Astronomy Expert Speaker Series, you can view the video recordings of our webinars at your convenience at our official ALP YouTube channel shown here. And here are the next upcoming speakers. Dr. Meg Urey, a professor of physics and astronomy at Yale University, will be touching on the supermassive black hole at the center of the Milky Way galaxy. Dr. Michael Kelly, who is a program scientist of the Planetary Defense Coordination Office of NASA headquarters and an astrophysicist at Yale University, will discuss the topic defending Earth from asteroid impacts. And Dr. Don Petty, a NASA astronaut who will be giving a very interesting talk on astrophotography from the International Space Station. And please wait for further announcements regarding these free online ALP talks at astrolinkfields.org and at our ALP Facebook page. Thank you again, everyone, and clear skies, and hope happy observing for T Coronae Borealis, and hope you make the discovery. Thank you again, and for the panelists, I will post the meeting, Zoom webinar meeting after this. Thank you.
Thank
Thank you
you,
so much,
everyone.
Brad.
Thank
you.
you,
Thank
Brad.
Brad, thank you, Brad.
Thank
Thank
you,
you so
Brad,
much.
for giving us a very good lecture. Thank you.